Welcome to my talk, an introduction to machine learning using Lego. But before we start, just a small bit about me. Who am I? My name is Jeppe, and I just love Lego. I am from Denmark, and as you probably know, Lego is from Denmark. So ever since I was a small boy, I just played with Lego. So much that one time my mother said, "Where is Lego gonna take you?" Well, apparently to London. I work as a consultant at a company called Itera. It is located many places in Europe with headquarters in Oslo, and I live and work in Oslo. Okay. I am guessing that all of you know Lego, and most of you have been playing with Lego. And maybe even some of you have been playing with Lego Mindstorms. I'm guessing I heard there was someone speaking Danish over there, so you probably have, and maybe some of you have as well. And Lego Mindstorms is what we are going to use through the next hour, where we will go through some very basic machine learning and see how we can apply that theory to make a Lego car steer by itself. Lego Mindstorms, if we go back to 1998, then the first Lego Mindstorms was released. And this is my first Lego Mindstorms set. It is called the Lego Mindstorms RCX. And if some of you are as old as I am, then you might. This was your set as well when you were small. And the good thing about Lego is that it lasts forever. But when you are working with computers, then unfortunately Windows XP is not working forever. And you need Windows XP to program this old RCX robot. So throughout this talk, I will use a newer revision of the Lego Mindstorms set. If you have been playing with Lego Mindstorms at some point, there's a good chance that you already have built a self-driving Lego robot yourself. There's a good chance that your robot looked a bit like this. It had tracks and a light sensor. And with this and a very simple algorithm, you can actually make this car drive by itself. If we use this simple algorithm, which says that when the light sensor sees black, then go left, otherwise go right. And it actually makes the Lego car here move, and it follows a black line. But this is not really a car. It would be fun if my car at home had tracks, but unfortunately it doesn't. It just has normal wheels, and the steering is a bit different, a normal car steering. So again, this works, but for a normal car, it doesn't really work. So can we, if we make another Lego car, which looks more like a normal car, it has a driving motor and it can steer, can we make that follow a black line in using an algorithm that looks more or less as the algorithm we saw before? Well, let's try. We use this algorithm. We start on one side of the black tape. We steer left, wait a bit, steer right, wait a bit, steer left, and so on. And again, it is more or less working, but the car is driving in a very wiggly motion. And again, it doesn't really look like it's driving like a normal car. So this might be a bit too simple. Here on the right, we see a promotion video from Tesla. And you probably know Tesla, and you probably also know that Tesla can do almost anything when it comes to autonomous driving. It can drive by itself, it can follow the road, it can take turns left and right, it can follow the car in front of it, and it can even park itself. And that might be a bit too advanced for us to make in the next hour. So let's pick a problem in between these two. Let's define our problem as we want a Lego car which looks more or less like a normal car with normal steering. We want it to follow a black line using, as I said, normal car steering, and we want to use as simple machine learning as possible. So that's our problem. Let us forget about Lego for just a second and focus on machine learning. First of all, it is important to note that we are all here for just 1 hour, so I'm not able to cover everything that has to do with machine learning. We're just going through some very basic theory. But machine learning can be used to solve many different problems. And there are also many different machine learning algorithms. And throughout this talk, we will just talk about supervised learning. And supervised learning, a definition for that is, I'm going to read, supervised learning is the machine learning task of learning a function that maps an input to an output based on example input-output pairs. Maybe that makes sense right away, maybe it doesn't. So let's have a look at what it really means. Let's say we want a machine learning model which can map an input, in this case a picture of an animal, to what kind of animal this is. We map an input to an output. We can also say that we map some features to a label. The definition said that in order to have a model like this, in order to develop this model, we need some example input-output pairs. Here's one example, and we are going to take a lot of examples into a magic algorithm. And this algorithm, magic, it's working. And out comes a trained machine learning model. And let's see what we can use this trained model for. Now, if we take a picture of a random animal from the internet, and apparently a random animal from the internet is a cat, put that into the trained machine learning model, out comes the label cat. So we take an input into the model, and out comes an output, or out comes a label. We can develop this model ourselves, but in particular for this problem, there are many good pre-trained models out there. For example, we can use Google Cloud Vision API. So let's try and do that. We take this picture of a cat, put it into the Google Cloud Vision API, and out comes a result. And yes, Google can tell us that this is actually a cat. And Google is pretty smart about this, so it can also tell us that it's a mammal, it has whiskers, and it gives us many labels. And again, you can train a machine learning model yourself, but when there exists pre-trained models which are really good, why bother? What we just saw was an example of classification where we map an input or some features to a limited number of categories. In this case, categories can be cat, dog, horse, and so on. Another type is regression. And supervised learning with regression, that is again, you have take an input, put into a model, and out comes a continuous value. So instead of a category, you get a continuous value. And we will take a look at that. For example, if we want to predict house prices in Oslo, then this is a regression problem. Because a house price, it's a continuous value ranging from, for example, 2 million Norwegian kroner to 100 Norwegian kroner. Here, the box of features, that's empty. And again, it's our input. What are we going to put into this model? We have to pick some features. And features for a machine learning model needs to be something that says something about the output that we want. So in this case, for example, the size of a house says something about the price of a house. I'm guessing also the number of rooms. If there are more rooms in a house, I would guess that a house becomes more expensive. And the same with the number of floors. So this is how we can select features. Hopefully, this definition makes a bit more sense now, and we can even rewrite it just a bit. So it says, supervised learning is the machine learning task of learning a function that maps a set of features to an output based on labeled training data. Okay, now we have used a trained machine learning model. But how do we actually come up with this model? Again, we can use a pre-trained model found somewhere on the internet from Google or someone else. But what do we do if we want to develop this model ourselves? Let's try and find a model which can map some features to a house price in Oslo. And we're going to reduce the number of features to just one. And we're going to do that just to make everything a bit simpler and to make it easier to visualize what we're going through in the next minutes. So we use just the size of a house, and we call that feature X. The definition said that we need some example data or some training data. And we have a lot of data here, where on the x-axis we have the house size in square meters, and on the y-axis we have the price of house. And what we need to come up with now is this machine learning function, which actually is our model. So a function that maps our training data in a good way. We also call this function a hypothesis. When we look at this data, it looks like there's a somewhat linear trend. So let's try and plot a straight line. Is this a good function for our data? Yeah, maybe. It looks like there's maybe too much data below the function than above it. So let's try another one. This one. Is it better? Maybe. So what we need to do is come up with the best function. And we do that by introducing theta 0 and theta 1. Again, remember that x here is our feature, so we call these theta values our feature weights. And our objective right now is to find these theta values. When we have the theta values, we have the function, and the function is our machine learning model. Okay, in doing so, when we're going to find these theta values, we introduce a notation where m is equal to the number of training examples and xy, yi is a specific training example. We also need to find the cost of a single training example. We see that here. And from that, we get the cost function. I'm not going into details of why the cost function is like it is. But one important thing to know here is that the cost function is, if we minimize that, then we get the best possible values for theta. So again, to get our machine learning model, we want to find the theta values, and to do that, we need to minimize the cost function. Okay, this hypothesis, this linear hypothesis, right now it has a single feature, and I can tell you already now that if we're going to make a Lego car steer by itself, a single feature is just not enough. So we are going to introduce more features. We're going to introduce features x1, x2, x3, and so on. And for each feature, there is a feature weight. So for all these x's, we have a theta. And as I said, this cost function, when we minimize that, we get the best possible values for all these thetas, and that is our goal. And we do that by using an algorithm called gradient descent. And again, I'm not going into details, we do not have time for that. But what I can say is that gradient descent works by doing some iterations, and in each iteration we get slightly better values for theta. So we repeat a number of times, and then we get some good values. And how many times do we need to repeat that? It's different from problem to problem, so we do not know that. And also, we have this learning rate alpha. We have that here. And this learning rate alpha, we do not know the value of this beforehand. And the number of repetitions depends on which value we give to alpha, the learning rate. We're getting back to this in a couple of minutes and see how it actually works. But right now, back to Lego. Because the main objective for this talk is, again, to make a Lego car steer by itself. So, of course, we need a Lego car. So I built this fairly simple Lego car. It has two motors, one motor for driving forward and one motor for steering. And it also has a sensor, so it knows that when the steering is in the most left or most right position. But a fairly simple Lego car. Yep. We need one more thing, because we have some machine learning, we have a Lego car, we also need some compute power to do all the calculations and to control the Lego car. So I built an app which can do all that. It has three different functions. It can collect data, it can train the model using gradient descent, and lastly, it can test drive the Lego car. Well, this collecting data, how do we collect data? Well, let's take a step back, and how, in general, how do one collect data when working with machine learning? And of course, it's different from problem to problem, but I'm guessing that most of you are actually collecting data for Google or Apple right now. I'm guessing that you have a smartphone. And when you are using, for example, Google Maps, you collect data for Google. If you are using Siri or you are using Google Assistant or something like that, you are collecting data for Google. Also, if we think back to the problem we had earlier of finding what is on a specific picture, we used the Google Cloud API and it worked, but where did Google get their data? Well, for example, if you go to crowdsource.google.com, you can actually help Google in identifying what is on pictures. I did that just to give it a try. When you sign up, you get questions you have to answer. And I got this question. Are there any buses in this picture? And I said, yes, there's a bus. And I thought, well, Google knows almost everything. So of course they do know that there's a bus in this picture. So is it a trick question or, yeah, I don't know. But then I got another picture with the same question. Are there any buses in this picture? And no, there are not any buses in this picture. So apparently Google didn't know whether or not there was a bus in this picture. They do now. But that leaves us with how are we actually going to collect data? And before we can answer that, we need to define our features. What kind of data are we going to collect? Well, we have this Lego car and we want it to steer on top of a black line. So this black line, is it a feature? Yes, it is. But what about the rest of the road in front of the Lego car? Is that a feature? Yeah, it is. So all of the road in front of the Lego car, that's our feature. So if I click collect data, we get to this page in the app. Where here we have the camera view, and that's what the camera sees. And I didn't say that. I mounted the smartphone in front of the Lego car. So this is what the camera actually sees in front of the car. And I said that the road in front of the car is a feature. It's not a feature, it's actually multiple features, because here we have multiple pixels, and each pixel, we could use that as a feature. But gradient descent that we saw before, when we have a lot of features, it becomes very slow. So I'm guessing that if we are using all pixels as features from this camera view, then it would take a very long time to compute our model. So instead, let's try. Again, I said earlier that we want this to be as simple as possible. So let's see how simple we can actually make it. Instead, let's try and define our features as just a single pixel row. There was. So let's use this pixel row here as features. And what you see below that, the picture here, that is actually just that single pixel row stretched in the vertical direction, just to visualize it a bit better. Okay, so now we have features. We use pixels as features. But what are we going to predict? What is our label? The label here, we can use the steering angle as label. So let us do that. Okay, we have defined features, we have defined the label, but still, we haven't talked about how we are actually going to collect this data. But we are going to do that manually. Instead of just placing the Lego car on top of the black line and says, well, I think now when the black line is going slightly right, then I think the steering angle must be X degrees. That's not really accurate. So no, I don't think that it would work. Instead, we're going to control it manually using a remote control. So I click collect data. I give the model a name, create the model, and every time I use the robot, whether it's for collecting data or driving, then it has to initialize the steering just to make sure that we are in the center position. Click Start Collect, and you can see now that when I'm turning the remote control, then the car is steering. Just one note here is that I disconnected the driving motor so the car wouldn't fall off the table. What you can also see here is that when I steer, this, where it is? There it is. This red line here, the vertical line here, that is the steering angle that I am actually steering. So now we can collect data. One other thing I want to say here is that the steering could be a bit faster. You can see that when I'm actually turning the remote control, it takes just a bit of time before the car is actually turning, is steering. And that is up to how I implemented everything. You can have a look at that yourself later, but it's not really a problem. Okay. Before we can collect data, we need a training course. So, to much happiness of the house's other residents, I removed all the furniture from the kitchen and decorated the floor with black tape. So now we have a training course. And now we just need to collect data. Again, click collect, give the model a name, initialize steering. I turn on the camera flash and start collect. The reason why I'm turning on the camera flash is just to give better readings. When I turn on the camera flash, the white part of the road becomes much brighter, but the black tape doesn't get that much brighter. So again, just to get better readings. You can see here that the bottom picture here, it updates quite slowly, but every time it updates, I collect one sample data. And we need a lot of data. So, walking around. And now you see that we collect mostly data going left. But if we want the car to be able to steer right as well, then we need to collect more data going the other way around. So I turn the car 180 degrees. And I continue. Okay, and what are we actually collecting here? let's take a look at that. Each row here is one sample data. So it's one label and all of our features. So on the left, our labels, that's the steering angle. Really not an angle. It goes from 0% when it's all the way to the left and to 100% when it's all the way right. And on the right, we have, as I said, all the features. So in this case, grayscale pixel values. Okay, we are done collecting data. Now that we have data, we need to calculate the model. So let's go back to the hypothesis and to this gradient descent. Remember the hypothesis we had earlier, this linear hypothesis. We can rewrite that just a bit to maybe so it gives a bit more sense to our current problem. So it becomes the steering angle is equal to theta 0 plus theta 1 multiplied with the pixel value of the first pixel plus and so on for all feature weights and features. And remember, our objective is to find these theta values. And again, to do that, we need to do gradient descent. And when we're doing gradient descent, we do not beforehand know the number of iterations, and we do not know this learning rate. So let's see how we find that. Okay, now I actually cheated a bit. So we are just going to test a very good learning rate here as a start. I know that a good learning rate for this particular problem is 1. So we're going to set the learning rate alpha to 1. Also remember that when we do this gradient descent, the cost function, we need that to get lower and lower and lower in every iteration. And to make sure that it really does that, we are going to plot it over iterations. So we have here on the y-axis we have the cost, and here on the x-axis we have the number of iterations. So now just calculate. We calculate 500 iterations, and again with a learning rate of 1. And we see here that gradient descent is working, because gradient descent is working when we get a lower and lower cost. And we see that we do that. Also, we see that the learning rate alpha is a good value now when it has a value of 1, because the cost, it converges. We see that it gets lower, 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 but it doesn't look like it can get that much lower now. So it converges, which actually means that we have found the lowest possible cost. When we have the lowest possible cost, we have the best values for theta. When we have the best values for theta, then we have a machine learning model. Okay, but as I said, I cheated a bit. This was not the first learning rate that I actually tested. So instead, let us test a small learning rate. Let's test a learning rate of 0.001. And again, we keep the number of iterations constant. So again, 500 iterations. And we start to train. And we see now that gradient descent is again working, because the cost is getting lower and lower in each iteration. But we also see that in 500 iterations, the cost is not really converging. It looks like if we ran for example, 1,000 or even more iterations, then we would come to a much lower cost. So again, it's working, but it's working slowly. And if we had a lot of features, or maybe we had even more training data, then this would be really slow. So again, finding a good value for the learning rate is essential. Now, some of you may be thinking now, why don't we just use an even bigger learning rate? It looks like when we increase the learning rate, then everything becomes faster. Okay, let's test it. We now use a learning rate of, we keep, again, number of iterations constant and use a learning rate of 2.5. And let's see what happens. Now, gradient descent is not working because the learning rate, the cost is not getting lower in each iteration. It does in some iterations, but in some iterations it increases the cost. And overall, the cost just gets bigger and bigger over time. So it's not working. And just for the fun of it, what about a very big learning rate? We try a learning rate of 100 and 500 iterations. What's going to happen now? We get an error. And we get an error because in the first iteration, the cost simply gets too big to be contained in a 32-bit float. So yeah, we get an error. Okay, we have collected data. We have trained our model using gradient descent. So the next is to test the car. I click drive. Again, initialize the steering. We always have to do that. Turn on the camera flash and start driving. Yep, and I was on baby duty, so. Okay, what we see here, besides that, it so far looks very good. If we take a look to the right, the app view here, it looks more or less like the view when we collect the data. We still have this camera view, and we have the pixel line that we are now not collecting, but using as input to our machine learning model. We still have that. And here we have a blue vertical line that is the predicted steering angle. So it worked. Hey! But we still have some 20 minutes left, so what are we going to do now? Okay, let's continue. Speed it up a bit. But no, something happened. Mini Tesla crashed. We let it continue. And again, no, went off course. So it looks like we have a model which is working, but it's not working perfectly. So yeah, we have to find out what's going on. It turns out that there are two different error situations. So the first one, we see here that the car is going left, but we also see that when the camera just sees about half of the black line, then the steering is not far to the left, it's more straightforward. We see that now, there it is. And that's not a good thing, because we wanted to turn sharp left, but now it's just going forward. So why is this? Yeah. Is there something wrong with our model? Remember that we chose a linear model, but there are many different models we could have chosen. So maybe the model is wrong. Do we have some bad data? Do we have enough data going left? Yeah, maybe not. And what about the hardware? Is it good enough? The camera, is it good enough? Does it see all of the road in front of the car? Maybe not. And here is another situation, again, going left, but then take a close look at the black line. Suddenly, the black line is not that black anymore. It turns gray. And when it's light gray, then the model doesn't know what to do. So again, it goes straight on. And that's a problem. Again, a bad model? Maybe. Do we have data for this? Okay. The last of these two problems, we can actually solve that very easy. There's a well-known technique, machine learning technique, called the curtain fall procedure, and we're going to implement that. And that's very quick. There it is. Now that is implemented. And this might seem like a joke, but working with cameras or physical sensors, then sometimes it's just easier to fix things on the hardware side than on the software side. So, quick fix for now. Let's look at our model. We go a step back and look at this problem where we wanted to predict house prices in Oslo. Here we have a linear function, and this is the linear function that maps all the training data in the best possible way. But what if we include the squared feature? Then we get a new function. And this new function, is it better than the linear function? Usually when working with machine learning, you would have some training data which is completely separate from, you would have some test data which is completely separate from the training data. And you would simply test the two models on the test data and see which one is performing better. But now that we're working with Lego, we are taking a more practical approach and just see which model is driving better. And just the changes that we're going to make for our problem. This is what we had before. The steering angle is equal to theta 0 plus theta 1 multiplied with the pixel value of the first pixel and so on. We now add all the squared pixel values. When we do that, we also get some new feature weights, theta. So when we do that, we can use the same test data, training data that we used earlier, but we need to do gradient descent again. And behind the scenes, I did that. So we are ready for a new test drive. So the only thing that we change now is the model. Still using the same data. Initialize the steering. Turn on the camera flash. Okay, and we see now that it gets further than before. So it looks like the model we have now is a better model for this problem. But now we drove mostly left. Let's try and drive mostly right. Let's see if it makes any change. Speed up the film and... Okay, it's never a good sign when, when there's some slow motion. So here, unfortunately, Mini Tesla crashed again.
Is it the same baby?
Yes, this I did this project over many years, so no, no, not the same baby. And as you can see, that climate changes has really hit Oslo. It is a warm winter. No, I made this last summer. Okay, so we have a better model, but everything is not perfect. So let's move on and see what else we can do. We talked about the hardware earlier. One simple thing, simple change we can do is to change the angle of the camera. So we point the camera a bit more down, so we see a bit more of the road closer to the robot. And hopefully that means that when we see the black line, when we go to the left or to the right, it doesn't disappear out of the image just as easy, hopefully. So let's see what we have done. We have fixed light conditions. We have tested a new model, which seems to be better. We have changed the hardware a bit. We have not tested that, so we do not know if everything gets better, but we have changed the hardware. What about this bad data that we talked about? Let's look at that. This is from earlier when I collected data. And note that when I slowed down the video, that sometimes the black line totally disappears out of the picture. And when we want the Lego car to steer after the black line, it's not good when you cannot see the black line. So that's bad data. And what we could do is to manually go through all the data and remove all training data which do not include the black line. We could do that. We're not going to do that right now, but we could do that. Okay. Now we have made some changes, and we have also made hardware changes. And when we have made hardware changes, we need new data. So I am going to run around in my kitchen again. And yes, I walked around in my kitchen for 20 minutes. Okay, now we have new data. And behind the scene, I ran gradient descent again using the new model. So we are ready for a new test drive. And suddenly the baby became younger again. So initialize the steering, camera flash on. And let's see if everything is better now. So far so good. Here we had a problem before. And even though it slowed down, we do not have a problem now. One thing you can note here is that the predicted steering angle, again remember that's the blue vertical line here, sometimes it goes all the way to the right or all the way to the left. So it looks much better now. So that was going mostly left and now going mostly right. it actually looks like we now have a Lego car which can drive by itself. Yeah. And that's just awesome. But when I did all this, I had a visit from my neighbor. And my neighbor, he asked me, "What are you doing?" And I said, "I'm working with Lego. Can't you see that?" And he said, "No, you're not. You're playing with Lego." He also said, "Well, it's quite cool what you're doing here, but it's going quite slow, isn't it? Can't we make it go any faster?" And I said, "I don't think so, but let's try." So here, the only difference is now that it's faster. I do know it's not really fast, but it is faster than before. I think it's 2.5 times faster. And we can see in the beginning, it's working fine. But when we get to sharp turns, then the robot becomes very, very wiggly. And now we will see that you're going all the way to the left, all the way to the right, and no, it doesn't work. And why is that? There are many reasons for that. First of all, the hardware here is not built for speed. The steering simply isn't fast enough. Also, collecting the data was done at a slower speed. So, yeah, many different reasons why this wouldn't work. Okay, what have we learned today? First of all, know your data. And in that, know when you have bad data. In our case, if we have data which do not include the black line, that's bad data, get rid of it. We also learned how to make a plot of the cost to find the best learning rate. And in that, doing gradient descent to develop our machine learning model. We also saw how to measure model performance. In the Lego case here, practical approach, but usually split data into a training set and a test set. And also, we can just make predictions within the limits of the training data. In our case, if we do not have enough data going very left, then the robot cannot go left. So, improvements. What could we improve here? Again, it's just improvements to a Lego car following a black line. First of all, more data. If I walked around my kitchen not just 20 minutes, but maybe for an hour, then more data. Maybe we would get a better model. Maybe we could try and collect data in different light conditions. Maybe we could even have an ambient light sensor and use the value of that sensor as a feature. Maybe. Maybe we could use more pixels as features. Maybe that would make the model better. We could also test other models, for example, a neural network or something like that. And along with the first point, if we could collect data faster, then in the 20 minutes we would get more data. Okay. We saw earlier that the problem that we solved was something in between the very simple problem and the Tesla problem. But it is more to the left, I would say. It's a fairly simple problem that we solved. So maybe next time we can do something more realistic. Maybe not Tesla realistic, but something in between what we just did and Tesla. And again, this is not something that we're going to do now, but if you, after this talk, say, hey, we want to build Lego, we want to implement some machine learning, and we want to take it a step further, then you can do, for example, something like this. Here we have 3 different roads. They have different surfaces, and they have different sides of the road. And we want a machine learning model which can drive here, steer the car here. What we can do, again, this is just some suggestions, is to split the problem up in 2 smaller problems, where the first problem is to find where is the road. So make a generic road, if you can say so. And from that, a machine learning model which can find the steering angle. Again, suggestions. But now, what is this? One more test drive? Why do we need it? Well, earlier, when we tested our new model with the new data and everything seemed fine, I tested the Lego car on the same course where I collected all the training data. And that's not really allowed. You need to test on new data. And in our practical approach, we need to test on a new course. So I converted all of my living room into a test course. And I can say that it is actually working. If you want to do some of this yourself, or maybe you just want to see what I did, then you can find the code for this app that I used throughout the talk on GitHub. If you have any questions, then come and ask them now afterwards. I think we are running out of time. So now, just thank you very much.